Hello dear students, welcome to my channel Explore Organic Chemistry with Anjali for BSc and MSc students. Dear students, yesterday we have seen the introductory part of the pericyclic reactions. In that reaction, we have seen that the various important features of the pericyclic reactions. Out of that, the most and utmost feature of the pericyclic reaction is the reaction takes place via concerted manner where the bond making and bond breaking, they are simultaneous. Bond making and bond breaking. Now whenever we talk about the bond making and bond breaking, so what is exactly happening? We know that this is a sigma bond, this is a sigma bond, and when it breaks you will get two different components or two different products. It means that when or this is I'm talking about the sigma bond. I'm talking about the sigma bond. In some cases we are using the pi bonds. We are using the pi bonds. So let us draw the pi bond. Let us draw the pi bond. Here the diagram is not very appropriate, but this is how the overlapping takes place when we see the bond formation. When we see the bond formation. So this is the story of bond formation. And whenever there is a bond breaking, I'm expecting the two different lobes where means two bonds get separated, two bonds get break down, they are breaking down, or they are broken, or they are broken. So whenever we are talking about the bond making and bond breaking, so in this case the pericyclic reaction, we can say that this is a concerted reaction and we have seen the bond formation and bond breaking. Now what is the theory is working, what theory is exactly working in the pericyclic reaction, what is the mechanism? The mechanism is totally based on the conservation of orbital of chemistry. Means we have to deal with the molecular orbital theory. So I am giving you some key points over here, that the molecular orbitals theory, how it works for the pericyclic reaction. So some complete mechanism is based on the mechanism is based on the conservation of orbital, that is the conservation of orbital symmetry, or some few points we can discuss over here, that is it is based on molecular orbital theory, basically. Molecular orbital theory. Alright. So let us see some key points for the pericyclic reactions for the molecular orbital theory. Let us see one by one. So here are some key points. These are some key points from molecular orbital theory. Molecular orbital theory. Now what are those key points? Let us see one by one. Let us see one by one. So the first point I mentioned over here, that basically there are two lobes for the p orbital. As we know that basically there are two lobes for p orbital. P orbital. And they have opposite phases. They have opposite phases. Now what is the meaning that we know these are the two phases as we have drawn. So this is the upper one, upper lobe, and this is the lower lobe. This is the lower lobe. Alright, so this is the upper lobe and this is the lower lobe. So usually the sign convention, we denote this as a, this is denoted as plus and this is denoted as minus, and the center atom is the carbon. So this is, I can put a little bit another. So this is a carbon. This is a center point is denoted as a carbon. Alright. So there are two lobes. This is the upper lobe. This is the upper lobe and this is a lower lobe. So I am talking about these two lobes which have opposite phase, means upper lobe has a positive phase and the lower lobe has a negative phase. They are not signs. Please remember, they are not charges. They are not charges. They are not charges. These are the sign conventions that which shows the wave functions, which shows the positive wave function as well as the negative wave function. So this is the positive wave function and this is the negative wave function. So the first point is two lobes for the p orbital, they have opposite phase. The upper phase and the lower phase, or upper lobe which shows the positive wave function and the lower one shows the, which I am giving minus, and the plus and the minus signs, these are not charges, please remember. So don't get confused with the charges. This is the positive sign and this is a simple negative sign which shows the wave function, positive wave function, wave equation, sorry, and this is the negative wave equation. Then considering this the structure of this lobe, the positive and the negative wave equation. Now whenever, so this is a single p orbital of the one carbon. It is a one carbon. This is a pi orbital of the one carbon. Now when two orbitals when two p orbitals, they are in a phase, so they interact and they form a covalent bond. So what is the meaning of when two orbitals they are in a phase? This is the extremely important term which always and always please remember this term, that when they are in a phase. Now what is the meaning of they are in a phase? Means the two orbitals of the carbon atoms, or for example I am giving you a couple of example that when the two orbitals they are in a phase. Suppose for example here it is a carbon carbon double bond, so please ignore the sigma bond, ignore the sigma bond, only consider the pi bond. Why? Because pericyclic reaction takes place via pi bond formation, via pi bonding. Pi orbitals are involved in the reactions, so only consider pi bonds here. Now let us see one carbon one. So I am drawing one the orbital for this. So this is a bond formation, and so this is a sigma bond and this is a pi bond. Now whenever both they are in a phase, that upper lobe overlaps with the upper lobe, lower lobe overlaps with the lower lobe. Now in this case we can say that the both lobes are in phase. Both lobes are in a phase. Then and then only the overlapping is possible and effective bond formation takes place over here. But when it means that the interaction is possible, interaction of the pi orbitals is possible when they are in a phase. When they are in a phase means the upper portion, the positive part overlap with the positive part of the another carbon atom, and the negative part overlaps with the negative part of the carbon atom. All right. So here when they are in a phase, that both the phases they are in a same phase. Now here I am putting the same sign over here, minus minus. So minus overlaps with minus and plus overlaps with plus. Then and then only effective bond formation takes place in all condition. So whenever there is a bond formation, please remember that the lobes are same. The lobes are same, means they are in a phase. Now another condition that we must remember, that when both lobes they are not in a phase, means if this is the story about they are in a phase. So this is the story about but when they are not in a phase, what will be the scenario? Now let us draw the orbitals, those which are not in a phase. So I am drawing the structure of pi orbital which is not in a phase. So they have exactly opposite. So their lobes are exactly opposite to each other. It means that the positive sign, they are just opposite to each other. So there will be no effective overlapping. There will be no effective overlapping. There will be no effective overlapping. So this is out of phase. Such overlapping is out of phase. So in the next topic we will see, this is called as effective overlapping and this is the minus overlapping. It means that if the interaction of two pi orbital takes place out of phase, we have to subtract from the bonding because there is a node formation. If such type of if this positive and this positive, they are opposite to each other, it means that there is a node formation. Now what is the meaning of node? Node is that particular point where there is a the possibility of availability of the electron is almost zero. Therefore in between such lobes we get the formation of node where the signs are exactly opposite, they are out of the phase because their lobes are at the opposite, they are placed in the opposite way. Plus and plus, they are in another way I can explain that above the plane it is plus, below the plane it is minus. This is above the plane is minus, below the plane is plus. In this case, in the phase we have seen that both are in the phase, both are in the phase, and in another case here we have seen that the plus sign, they are in the opposite planes and minus signs are also in the opposite planes. So there is a formation of node over here. So in this case the node has been created. I hope you understand this concept. When basically there are two lobes, let me explain once again. Basically there are two lobes, of the pi orbital, and those pi orbitals, they have opposite phases. Means that this is your first phase, that is plus sign, and this is your minus sign. I can say that in another way, lower lobe in the below the plane, upper lobe is above the plane. Alright. So when these two orbitals, I am considering the CC double bond, and I have drawn these two diagrams for when two orbitals, they are in a phase. What is going to happen? It means that there is an interaction of pi orbitals. Plus orbital interact with each other, minus lobes interact with each other. So this is the effective overlapping where the bond is going to form. But when the pi orbitals, they are not in a phase or they are out of the phase. What is the meaning of that? One carbon lobe shows positive lobe at the above the plane and negative lobe at below the plane, and the another carbon has the negative lobe above the plane and plus below the plane. In such cases the effective overlapping is not very attractive or not very smart or not very it is not hardly possible to have interaction with each other. In such cases both lobes, they are not in a phase, so there is a formation of nodes. Now what are nodes? Nodes are nothing but the area where the possibility of existence of or probability of finding of electron is almost zero. So this condition occurs when the lobes are not in a phase. So please remember, this is the scenario. I hope you understand, because this complete in a phase and not in a phase, this concept we carry over for the effective overlapping. Effective overlappings means we have a effective interaction. Effective interaction will lead to formation of effective bond formation. So these are the various important terminologies in the pericyclic reaction, that is the in phase and out of phase. Overlapping of pi orbitals in phase, overlapping of pi orbitals when they are not in a phase. So this is how the scenario. Now let us see the another important point for the molecular orbital, that is the electrons fill molecular orbitals according to the same rule. Means electrons, whenever there is a electrons fill molecular orbitals according to the following rules. Means the filling of electrons will be same as in the atomic orbitals. So molecular orbitals can be filled just like the atomic orbitals. Now electrons fill molecular orbitals according to the same rule, and what are those rules? We'll see one by one. That governs the how they fill the atomic orbitals. Now how the atomic orbitals are filled? Let us see one by one. The one is, it can be the electron goes into the available molecular orbital with the lowest energy as per the above principle. What is that? Our principle says that an electron goes into the available most molecular orbital with the lowest energy. So let us write down, an electron goes into the available one, or you can say that available molecular orbital with the lowest energy. Alright. Now what is another principle? Another principle is the Pauli's exclusion principle. As per the Pauli's exclusion principle, only two electrons can occupy a particular molecular orbitals, and they must have the opposite spin. So the spin is different. So only two electrons can occupy a particular molecular orbital, and they must have opposite spin. If they have parallel spin, it will become unstable. So opposite spin make them very stable, and they can stay in the same orbital, or they can stay the same house. This is a Pauli's exclusion principle. And what is the third rule? Third rule is the Hund's rule. As per the Hund's rule, what it says? Hund's rule says that an electron will occupy an empty degenerate orbital before it will put up into the higher state, before it will be pair up. So an electron will occupy an empty degenerate orbital empty degenerate orbitals before it will pair up, before it will be pair up, it will be pair up. Now we know that in the p orbital there are three degenerate orbitals, px, py, pz. They are having same energy. So the electron will be filled up like this, for example. So if there are 4 electrons, so they will not be filled up like this. They will not be filled up like this. How they will filled up? That the first electron will go to px, another will go py, the next one will go, the third will go to the pz, then the fourth will come to the px. This is how the Hund's rule says. Now next point which is very important over here, that here we have explained how the electrons feel on the in the molecular orbitals. They are just like they are filled in the molecular orbitals just like atomic orbitals, and they are governed by 3 principles: Above principle, then Pauli's exclusion principle, and the third one is the Hund's rule. Next, in the next point, another next point, what is important? Each carbon that forms a pi bond has a pi atomic orbital, and pi atomic orbitals of the carbons combine to produce a set of molecular orbitals. Now what is the meaning that? Let us write down the third important point for the molecular orbital theory, that each carbon that forms a pi bond, each carbon which forms a pi bond, has pi atomic orbital and pi atomic orbital of the carbons combine to produce a set of molecular orbital. So pi atomic orbitals are responsible for the formation of pi molecular orbitals. So 2 pi atomic orbitals of the carbon atoms, they interact with each other and they form the molecular orbital or set of molecular orbital. Carbons, they combine to form a set of molecular orbital. In this way, we can get the formation of molecular orbitals. Thus, molecular orbitals can be described by the linear combination of atomic orbitals. Means one pi atomic orbital of the one carbon atom and another pi orbital of the another carbon atom, they combine to each other and you will get the a set of molecular orbitals. So this combination is called as linear combination of molecular orbitals. Linear combination of, sorry, atomic orbitals. Linear combination of the atomic orbitals. This is how we can explain. So all molecular orbitals are, this is also called as LCAO. Uh, they combine with each other and they will get the set of molecular orbitals. So LCAO is responsible to form the molecular orbital. Please remember. Then the next important point we must know that in the molecular orbital, each electron that previously occupied at the pi atomic orbital belonging to an individual carbon atom now occupies the entire part of the molecule that is encompassed by the interacting pi orbital. Now, this point I can explain with the help of this diagram. Now, here I am not drawing. So this is the plus and minus plus here. So these are the two lobes. So this is a linear combination of atomic orbitals. These are the atomic orbitals. This is a pi atomic orbital. And after formation, you will get the combination of this one. So this is a lateral overlapping over here. This is a lateral overlapping. Alright. Now here, these are the molecular orbitals. These are the molecular orbitals. Now the electron from here, and electron from here, they will combine to form this one. So here one electron, here one electron, and here you will get the formation of molecular orbital. So this can be denoted as a function psi. This molecular orbital is denoted as the wave function psi. Alright. So in molecular orbital, each electron which is present over here will combine and you will get the new molecular orbital, and this molecular orbital is paired up with, as per these three rules, we know that. So by the Hund's rule, the electron will go in the, they have a opposite spin and they occupy in the same molecular orbital. Then the next topic is where how the mechanism takes place in the pericyclic reaction. So the mechanism of pericyclic reaction, as I told you that the mechanism doesn't influence by any radical formation, any ionic formation like carbanion, carbocations or carbenes or nitrines, etc., etc. So how does the mechanism proceed in the forward direction, or how the mechanism happened in the pericyclic reaction? We know that the complete concept is based on interaction of pi orbital. So mechanism of pericyclic reaction is very, very interesting, and this is a totally different mechanism we can see over here. Now there are three methods which explains the method or analysis of the mechanism. So the methods of analysis are methods of analysis of the mechanism. Methods of analysis of the mechanism, they are based on three main concepts. First theory is the conservation of orbital symmetry. First is the conservation of orbital symmetry. Orbital symmetry or orbital symmetry correlation, or it is also called as orbital symmetry correlation. I In the last lecture I have explained the electrocyclic reaction as well as we know that those reactions are there. In those reactions the reaction arrows are like this. So in the reaction moves in the forward direction, the reaction also moves in the backward direction. So in such cases the reaction it means that bond breaking and bond opening. If there is a ring formation, so ring can be open also. If the reaction gives you ring closed, so it can be opened, it can be closed in all the in all. So both concepts can be happen in the pericyclic reactions. Now in such cases what is happening? So we have to explain the exact mechanism takes place over here, where whenever there is a ring opening or a ring closing, there should be a conservation of molecular or the symmetry of the molecular orbitals. If we change the symmetry of the orbitals, it means that the the original molecule will be changed. So in such cases we have to explain the mechanism how the conservation of orbital the symmetry of the orbital take place in such reactions. Now how they are so this concept is given by R.B. Woodward and Roald Hoffman. In 1965 it was when it was introduced, the same concept has been introduced at the same time. The what is the second method over here? The second method is the frontier molecular orbital method. This is the frontier molecular orbital method. This is also called as FMO. FMO method. And this method, in which we know this terminology, that is the HOMO and LUMO, means highest occupied molecular orbitals, lowest unoccupied molecular orbitals. This method was given by Kenichi Fukai. It was given by Kenichi Fukai. And the third method is the, so let me explain the third method. Which one is the third method? Method is the Huckel's-Mobius method, that is the HM method, or the perturbation of the molecular orbital method, means PMO method. So let me explain the Huckel-Mobius method, which is also called as HM method, or this method is also called as perturbation method of molecular orbital, perturbation of molecular orbital method. So who has given this method? Who has explained this method? This method was explained by, or was invented by, given by H. Zimmermann and Dewar. It is given by H. Zimmermann and Dewar. So with the help of these three methods, we can explain the mechanism of the pericyclic reactions. So the detailed mechanism and the methods will be explained in the next lecture, but time being I am giving you some guidelines for the uh, how to draw pi molecular orbitals in the various Paulins, Dines, conjugated system, etc., etc. So here these are the three methods are used to find out or to analyze the methods which are associated with the mechanism takes place in the pericyclic reaction. Now, how to draw the pi molecular orbital diagrams? There are some guidelines. So with the help of these guidelines, we can easily draw the various molecular orbitals for the various conjugated system. So I am giving you one by one. So here the first, so let me give you some important guidelines. So the heading, some important guidelines we have to follow while drawing the molecular orbitals. Important guidelines. Now what are those important guidelines? Let us see one by one. Let us see one by one. So the first important guidelines is the number of pi molecular orbitals which are formed equal the number of carbon atoms. Means the, so I am giving with example, I am explaining with example, but let me first write down this rule number 1. This is the rule number 1. The number of pi molecular orbitals which are formed are equal with the number of carbon atoms involved in the conjugated system. Then another sentence I will explain with the example. Half of these are bonding and other one is the anti-bonding. Half of these are bonding pi orbitals and the other half is anti-bonding. So I can denote it as a pi star. Now with the example I can explain you this rule number 1. So let us see the example how it can be explained. Now with this rule number 1, let us see the one example, that is the ethylene. Let us see the examples of ethylene. Now ethylene means CH2 and CH2, right? So how many double bonds are present in the molecule? Only one double bond. So let us analyze the molecule first. Now I always told you that whenever you have a molecule, please analyze the molecule. So try to analyze the molecule first. How many double bonds are there? How many sigma bonds are there? Sigma bonds 1. Double bond or pi bond 1. So we we don't need to consider about the sigma bond, as no sigma bonds are involved in the generally in the pericyclic reaction. We are only considering the pi bond. So let us consider the pi bond. So only one pi bond is there and two pi electrons. So one pi bond, it means that how many pi electrons are there? Atomic orbitals. So if there is a formation of one pi bond, so how many pi electrons are involved or atomic orbitals are involved? So with the help of two atomic orbitals, you will get the formation of alright. So here, as there are two atomic orbitals, so here two molecular orbitals are formed. So two atomic orbitals will give you two molecular orbitals. So how they will give you two molecular orbitals? Let us see the molecular orbital diagram for this. So this is the carbon number 1, this is the carbon number 2, this is so here I am drawing one electron present over here, one electron present over here, and so here is the formation of, this is a molecular orbital, this is the atomic orbital. So here, so this is a one atomic orbital, molecular orbital, this is the another. So this is called as bonding. This is called as bonding atomic or molecular orbitals, and this is called as anti-bonding molecular orbital. So it can be denoted as psi1 and this can be denoted as psi2. So this is how the meaning of this this point number 2, point number 1, that is the number of pi molecular orbitals which are formed. So if there are two pi orbitals, so there will be two molecular orbitals. One is bonding, another one is the anti-bonding. So half will be the bonding, half will be the anti-bonding. Suppose there are 4 atomic orbitals, so there will be 4 molecular orbitals. If there are 4 atomic orbitals, there will be definitely 4 molecular orbitals, and half of them, 2 will be bonding and 2 will be anti-bonding. 2 will be here 2 will be bonding atomic orbitals and 2 will be anti-bonding atomic orbitals. This is how I can write. Alright. For example, there are 8 atomic orbitals. For example, there are 8 atomic orbitals. So for 8 atomic orbitals, let us see. If there are 8 atomic orbitals, so definitely there will be 8 molecular orbitals. There will be 8 molecular orbitals. And out of that, 4 will be bonding and 4 will be anti-bonding. 4 will be bonding atomic orbitals and 4 will be anti-bonding atomic orbitals. So this is how the scenario. If suppose there are 16 atomic orbitals, for example, there are 16 atomic orbitals, so definitely there will be 16 molecular orbitals. Out of that, the 8 will be bonding atomic orbitals and 8 will be anti-bonding atomic orbitals. Now I hope you understand What is the meaning of this first point is the number of pi molecular orbitals which are formed equals the number of carbon atoms in the conjugated system. Half of these are the bonding and other half will be the anti-bonding. Then the next guideline is extremely important, in which that in the linear combination of atomic representation of the pi molecular orbitals, draw the lowest energy orbital with no nodes. Now what is the meaning of that? In the LCAO, linear combination of atomic orbital representation, of the pi molecular orbitals, draw the lowest energy orbital, with no node. Energy orbitals with no node. Means zero node at all. Means there is a zero node at lowest energy. This is what the meaning of the sentence, this rule. I'll explain. Zero node at the lowest energy, and then when all the p orbitals are in a phase. Now I am drawing this particular, this is the linear combination representation. Now how I can draw this, because I have to put the plus and minus sign over here. If all plus signs are in the one side and all minus sides are another side, so there will be zero node. So I can put the number of node is equal to n. N is a number of nodes. So n is 0. There will be no node as such. Means the linear diagram is like this. Complete linear diagram is like this. Alright. Now if I want to put one node, so what is going to happen? So this is the lowest one. This is the lowest one, means psi 1. If I want to draw the psi 2, how can I draw psi 2? As we move in the higher energy level, the number of node will be increases. So I need to put one node. It means that first of all I can draw this combination, and I've put one node over here. So if there is a node, so the plus sign over here, I can put the plus sign in the opposite direction. Now there is a one node, means psi 2 n is equal to 1. Now let us move towards the psi 3. Psi 3, again I am drawing the 4 lobe. Now here I can put the psi 3, the number of nodes will be 2. So here I can put 2 nodes. So whenever there is a node, I am putting the opposite signs, and there will be no node in between these two, so they are in a phase. There is one node, so they are out of phase. Out of phase means the opposite direction. So n is equal to, here n is equal to 2. N is equal to 2. Now let us see the fourth one, that is a 1, 2. I am just explaining, I will explain the 1,3-butadiene later on, but this is how the nodes can be drawn. So here I can put a psi 4. Here everywhere I have put the nodes over here. So there is a node in between these two lobes. So I can put plus over here, minus plus here. minus here, minus here. Here also with respect to this minus, there is a node in between these two lobes. So I am putting plus minus over here. Now in between these two lobes, there is a node. So I can put minus here and plus over here. And number of nodes will be 3. So if there is n is the wave function, how many number of nodes will be present? They will be n minus 1. For you have seen that for psi 2 there will be number 1. For psi 3 number of nodes are 2. For psi 4 number of nodes are n3. If I have, so without drawing the orbitals, you can easily calculate the number of nodes. If I have psi 5, the number of nodes as per n minus 1, number of nodes will be 5. If I have psi 6, the number of nodes will be 5. If I have psi 7, number of nodes will be 6. So this is how you can easily calculate the number of nodes also. So here I need to complete the sentence that in a LCA or linear combination of atomic orbitals, representation of the pi molecular orbitals, draw the lowest energy orbitals which do not have any nodes at all. And whenever you move in the next level, put one node another. Next level you can put the number of nodes, so forth, number of nodes in the increasing order, so forth. Right. So this is how you can put easily the number of nodes in the wave function. The third important point is the place the vertical nodes separating the p orbitals, so that, yes, how can you, I have just explained you that how can you put the node. So here also the modus operandi is explained over here. Place a vertical node, where we need to put a nodes which separating the pi orbitals, so that number one, they are asymmetrically arranged along the molecular backbone. Now as I told you that this is a backbone, this is the backbone. So this is the, with the pink line I am just marking, this is the backbone of the carbon. And if there are 4 carbon, so these are the, I am putting 4 dots over here. I am putting 4 dots over here. So these are the 4 dots. So this is the chain, this is a backbone, we can easily understand. So whenever you draw the backbone, now here they are asymmetrically arranged along the molecular backbone. So how you can put, they are asymmetrically arranged, along the molecular backbone, Then what is the second point to be remembered? There is a maximum number of adjacent p orbitals in the phase. There is a maximum number of adjacent pi orbitals in phase. Third one is the nodes are separated as far as possible. The nodes are separated as far as possible. So these are the important points, and the first and the last most is the energies of the molecular orbitals increase with the number of nodes. Means if n is equal to 0, it is the lowest energy molecular molecular orbital. If n is equal to 1, so you place this orbital little bit higher position. Then the n is equal to 2, next higher. Likewise, you can if the energy number of node increases, the energy of the molecular orbital increases. So the energies of the molecular orbitals increases with number of nodes. This is also an important point. Number of nodes. All right. For example, if we have psi1, if we have psi1 and psi2, which one has higher energy? Psi2 has higher energy than the psi1. Right. So this is how you can easily explain. You can, with the help of these guidelines, you can easily draw the molecular orbitals of the. So I am just giving you these important guidelines, and then next few minutes I will teach you how to draw the molecular diagrams of the conjugated system. Other than that, there are related to symmetry also, as we know that the conservation of symmetry is also mentioned over here. So two factors are involved over here. C2 symmetry, that is a center of symmetry. Center of symmetry means you rotate the molecule. For example, this is the, so this is like a molecule, and I am applying the C2. I am applying the C2 means how I should apply this. Yes, if I rotate this molecule in a two way, so first rotation will be like this, and another rotation will be like this. So after C2 rotation, I am obtaining the identical molecule. So I can say that this molecule have C2 plane of symmetry. Now mirror plane symmetry means, for example, this, if this is the lobe, this is the molecular orbital. So now here, if I put the mirror in between these two, so I am getting exact identical images. So as per C2 here, this is a symmetric one. Now here, what is happening? If I put this molecule in between, I put the mirror, I am getting the exactly identical mirror images of each other. So they are symmetric with respect to, so mirror plane symmetry and the C2 symmetry, these are the two symmetry factor. So, or here you can say that sigma. So sigma is a mirror plane symmetry. So C2 plane of symmetry and mirror plane symmetry, these are the two factors we have to consider while drawing the molecular orbitals. And okay, now come to the actual how to draw molecular orbitals of conjugated system. Now the main topic is how to draw pi molecular orbitals. Pi molecular orbitals. So till now we have seen that if there are two atomic orbitals, so there will be two molecular orbitals. Out of that, one is antibonding, another one is bonding, another one is antibonding in the molecular orbitals. This is the one thumb rule. Another rule is if the lowest molecular orbitals, they have a 0 nodes, and higher one, they may have more than 1 nodes. The third point we have seen that the factor, that is C2 and the mirror plane, these are the two factors we need to introduce while drawing the molecular orbitals. Now before that, how to draw molecular, you must know the, now I am giving you question number. In this question number, let us see how many pi molecular orbitals are formed in. So let us see one. First one is the ethylene. Second one, it is a 1,3-butadiene. 1,3-butadiene. C is 1,3,5-hexatriene. So let us see the solution. Now for the first case, this is the formula of ethylene. So how many pi molecular orbitals are there? There are 2 pi molecular orbitals. Atomic orbitals are 2. So molecular orbitals will be here I am just asking you how many molecular orbitals are there. So there are only 2 molecular orbitals. Now here 1,3-butadiene. So in 1,3-butadiene, this is one pi bond, this is another pi bond. So how many pi orbitals are there? There will be 4 molecular orbitals. So this is B. What about the hexatriene? Hexatriene, so this is the structure of hexatriene. How many molecular orbitals are involved? Here 6 molecular orbitals are involved. Means 2 pi electrons will make one bond. So how many electrons are there? 6 electrons are there. So 6 molecular orbitals are involved. Here how many electrons are there? 4 pi electrons are there. So 4 molecular orbitals are involved. 2 pi electrons are there. So I am drawing. So here that will be the better thing, because ignore the sigma bonds. So here 2 pi electrons are involved. So number of molecular orbitals will be 2. Here 4 pi electrons are involved. So number of molecular orbitals will be 4. Here 6 pi electrons are involved. So number of molecular orbitals will be 6. Now in the next lecture, we will draw the various molecular orbitals of 1,3-butadiene, 2,4-hexadiene or 1,3,5-hexatriene, etc. etc. Actual molecular diagrams will be drawn in the next lecture. So let us revise. The things will be like that. You should draw the molecular diagram while considering the atomic orbitals. Linear combination of atomic orbitals will give you the same number of molecular orbitals. Then you have to consider the number of nodes are present. If psi n is the number of orbitals, molecular orbitals, so number of nodes will be n minus 1. At the same time, you have to apply the C2 plane of symmetry and the mirror plane of symmetry. So these are some important points we need to apply while drawing the molecular orbitals. So in the next lecture, I will teach you how to draw the molecular orbitals of the conjugated system. If you like this lecture, please press the icon of subscribe and like the button, press like button and share this lecture to your near and dear. So thank you so much.